We'll review now some basic properties of exponentials. We'll go into more detail in later submodules about how to solve exponential equations and use them for modeling real-world phenomena. But for now, we'll suffice to review some mathematical theory. So what is an exponential? Well, we've sort of seen them already. It's anything where I write it as a number raised to another number. Now, we call x the base and y the exponent. So typically it's written as base to the power exponent. So we've already seen some of these. The terms of polynomials fit into this regime, right? For example, x squared fits into this. In general, x to the n has x in the base and a constant n in the exponent. So if you're thinking about the base being variable and the exponent being held constant, we've already begun to analyze these. These are the atoms of polynomials. These are the powers of x you use to build them. When people refer to, say, exponential functions, however, they typically mean something else. They actually mean that the base is constant and the exponent is variable. So something like 2 to the x. Okay, so here the base is constant at 2, but the exponent is the variable. And this is what they mean when they refer to an exponential function. Okay, so some exponential functions that you ought to be familiar with. Would be things like 2 to the power x, maybe 10 to the power x, and then this number e to the power x, which we'll discuss a little later. Now, e is just a special number. It's equal to approximately 2.71. The reason it gets its own letter, kind of like pi, is it has very special properties in calculus. It fits very nice theories. So it's sort of studied in its own right. For us, we just think of it as a special number with a particular decimal expansion. So like 2.71. So let's look at some of the basic properties. The first three are, or I guess really they're all very important, but I would say that for the CLEP, this one is just indispensably important. So this says that if I have addition in the exponent, I can break that up as the first exponent times the second exponent, but outside of the exponentiation. So for example, 2 to the power x plus y is equal to 2 to the x times 2 to the y. And you can use this to do some nice computations. For example, we already saw 3 to the fourth. You can write this as 3 to the 2 plus 2. So 3 squared times 3 squared, so 9 times 9, so 81. So this is actually a little bit easier to handle, I think, than trying to do a bunch of iterative multiplications. Another nice one is, what happens if I have the same exponent but a different base? So if I have a to the x times b to the x. Well, this is the same as if I multiply the bases and then exponentiate. So for this one, you could say something as an example like 2 squared times 3 squared is equal to 6, which is 2 times 3, squared, so 36. But you could also have done this calculation without this trick. You could have said 2 squared is 4, 3 squared is 9, and 4 times 9 is 36. Another important property is what happens when you iterate exponents. Or another way of saying this is, I exponentiate once, and then I take the result and I exponentiate again. Is there a simple way to deal with this? And the answer is yes. Instead of doing one exponentiation and then another one, I can actually just multiply the exponents and do one exponentiation. So here I have a to the x, and then I raise it to the yth power. That's what these parentheses indicate, is that first, following the order of operations, I do what's in the parentheses. So I do a to the power x, and then I raise it to the yth power. So the iterated exponentiation's on the left side. On the right side, I have the product of the two exponents, x times y. So for example, 2 squared to the third could just be written as 2 to the sixth. And then we can continue to write this out if we want. This is 2 to the 3 plus 3. So that's 2 to the third times 2 to the third. So 8 times 8, so 64. So in many cases, these exponential rules can be stacked together. I can use one to make an initial simplification and then use others to do even more. Now the last one is what I call a convention. It doesn't really have a whole lot of mathematical content. It just says that anything raised to the 0th power is 1. So x to the 0 equals 1. So I see this right here. So for example, 2 to the 0 is 1, 10 to the 0 is 1, e to the 0 is 1, anything to the 0th power is 1. So let's look a little bit at plots of exponential functions. This will be, again, studied a little bit more later, but I think it's good to get a feeling for it now. Now we've seen what degree 2 polynomials look like. They look like these parabolas. So that's what x squared looks like. What about 2 to the x? When I switch the role of the exponent in the base, does that change the picture a lot? Extremely. They look totally different. So an exponential function looks like this. At the value x equals 0, this is y equals 2x. At the value x equals 0, I get 1, and then I get very rapid growth. In fact, it gets its own term. This is what exponential growth looks like. Extremely rapid. So as x gets bigger, I get extremely rapid growth. And then as x gets smaller, I get rapid decay to 0. Now, in this case, I don't actually ever hit 0. In fact, I get arbitrarily close to it, but I never get there. This is what's meant by exponential decay, is moving towards 0 very rapidly, but never actually getting there. So another good picture to have in mind is the mirror image of this, where instead of having y equals 2 to the x, I have y equals 2 to the minus x. So again, at x equals 0, this is 1. And now here, I have rapid decay towards 0. And here I have rapid growth as x gets more negative. In a later submodule, we'll give a general theory for how switching x with negative x changes the picture. In this case, we're just doing a mirror image over the y-axis. So now, we haven't really discussed how to use exponential functions for modeling or for describing real-world phenomenon. We will do this in a later module. But just from these pictures, I think you can get a sense of how this is useful. If I have some real-world quantity that grows extremely rapidly or decays extremely rapidly, perhaps an exponential model is useful. So sometimes these are used as starting blocks for models in, say, biology, where I have a population of animals and I know it grows by, say, doubling over a fixed period of time. Then an exponential model is ideal for this. You also see this often in physics and chemistry. The classic example is looking at a radioactive material that decays. You can measure how much decay has happened by using this exponential decay model. So these ideas are really foundational for all sorts of real-world problems.